I've known Otto for 40 years and followed his work. In fact, Otto, I think, is the longest tenured faculty in this department. Only person that's been here longer than me, I think. But unlike me, he's maintained his ability to question, his ability to push the boundaries. I don't have his lists of accomplishments in front of me, and if I say I can't pronounce some of the Dutch things, I apologize. If I said them, I would get them wrong. So I'm going to just turn it over to Dr. Strack and have him talk about his most recent work.
Thank you, Randall. Okay, I'm going to talk about fractured rock. And I'll also tell you how I got the first introduction to fractures in rock. When I came here, I was introduced to Douglas Barr, who was then the president of Barr Engineering Company. And he invited me to come once a week to Barr Engineering to have discussions with him and his employees and give seminars. And it was a very nice relationship, actually. Doug and I became very good friends. But I was there one day, and at Barr, they were doing tracer tests of groundwater. And he told me that they injected some of that tracer in one place and got way before expected it kilometers away showing up. So he said, well, that is because this is karst, and we have large fractures, and then when the water gets into the fracture, it moves very quickly. So he asked me whether I thought you could ever model such a thing, and I didn't think so. Same thing with Calvin Alexander from Earth Sciences, who studied these things, mostly all his career, I would say, probably. So I came to the conclusion that maybe you can model it, and that's what I want to talk about today. So it's going to be about three-dimensional flow in fractured rock. And because you're probably going to say, what the hell, but why would you do this? What's the point? And so I have to give you a motivation, because there is a point. So we have at the moment a really crisis in groundwater. There is severe shortage. I was at the Mud Flow and More conference. It's a large groundwater flow conference. This was in Princeton. And the main topic was the crisis in groundwater. And there are two problems. One is that you're getting less and less. There's a very severe depletion that we don't seem to be able to deal with. The way we deal with that problem is that we drill the wells lower and lower until they're dry. And that's not really a good solution. So that's one issue. And the other issue, and they were both brought up by somebody from the Ag department in Washington. And the second problem is that we have way too few experts in the field. So we were all told, many of the participants are professors and teaching groundwater. So we were told you have to recruit people, because pretty soon everybody is going to know about this, not because there's no water to drink, but because there's no food in the grocery store. The biggest user is agriculture. And if you have no water, we will have to face the consequence. So this is a real problem. So that is the motivation, because we now we can't just say, well, I'm not going to worry about fractured rock because it's a nasty aquifer. We don't know how it's flowing and how to deal with it. Because you don't have that luxury. We have to deal with any kind of source of groundwater. So there's aquifer depletion. This is from a talk I held in the same room, same series, 10 years ago about groundwater. In the Ogallala aquifer, the groundwater levels were down then, 10 years ago, 150 feet down. It's not going back up, it's just going down. And you see where the problem is. The agriculture is by far the largest user. So we really have to do something about it. And what I thought might be helpful is to investigate a possible resource that we haven't really used much, namely discrete fracture networks that are there, southern Minnesota, northern Minnesota, Sweden. We have to learn how to deal with these, and we don't know, we have no clue. Fracture flow is poorly understood. There is, at the moment, except what I'm going to show you today, not a really good model for it. So there are no full-scale models. And field investigation is very difficult. So this is a section, I'm cheating, because this is a two-dimensional model made by Eric Toller, who is my co-author. I should say at the beginning that this is a cooperation between Eric and myself, and that he is the one who's doing all the programming, at least until now. So this is a two-dimensional model that he published in Water Resource Research some time ago. But I can also just tell you this is a vertical section of a three-dimensional one. And the problem is that if you drill through it, so this is a drill hole, then what you collect is water from all these different fractures, but you have no idea from which ones. So you get water out of it, but it doesn't tell you anything. In fact, it tells you nothing. It tells you that you get water out of the aquifer, and that's it. So what I'm proposing is follow the example of Cundall and Strack. In the early 70s, we started this. It was funded by the National Science Foundation, based on the distinct element method, which is dealing with distinct, not discrete elements. I'm still angry that people have renamed this behind my back, because I named it distinct element method after a lot of thought, because this was about separate particles, right? So they're distinct particles. Discrete elements, all numerical models have that. So I keep, slowly it's coming back, the name, but anyway. But that I want to follow it. We have the same problem as we had still have in soil mechanics. We don't know about the medium. We have to do testing numerically. That's the only way we can compute velocities, discharges, pressures, hydraulic heads. We have to do it that way. So the model that I'm describing here is that the medium, the matrix, is impermeable. All the flow occurs in the fractures. We might be able to relax some of these things, but at the moment that's what it is. And the medium, the rock, is incompressible so that we can deal with transient flow in this system. So how are we going to do this? Let me first give, this is the simplest version of this. This is two fractures. I should tell you right from the start that they're bounded in this model by circles. They look like ellipses because it's three-dimensional. And the flow is in each of the fractures that we can actually describe with some approximations. And the communication between fractures is via intersections, which are lines that are in part of, or fully lines that go from one boundary into the other, or just part of the intersection. So, but what's happening there is really complex. And it's also strange, and it took me a while to figure it out. So I made a very simplified model of this. So this is two planes. They are fractures, approximations, a plane alpha and a plane beta. And there are discontinuities in velocity, normal component of flow, across that blue line, which is where the two planes share. Right? So that's where they are connected. So the green arrow is in the green plane, alpha, and you see it's discontinuous because part of its flow goes out into plane beta. So there are discontinuities from alpha to alpha, from alpha to beta, from beta to beta, from beta to alpha. So it's very complex, and the division of flow depends on conditions, and the conditions are continuity. We don't want to create any water here. It should be just from flow, and then we should be able, what we have, the goal is to compute what's the flow and the pressures and everything else. But that is the idea. So here, in this case, I made it very simple. I said, okay, we'll put a source in plane alpha and a sink in plane beta, or the other way around, I don't remember. So when you then look at plane beta, the blue line is the slot. This is the slot where they are connected. This is the source or sink. It's impossible to tell, and there's a source on the other side, and it's producing to the sink. And the heavy blue line is where the discontinuities are in the normal component of flow, and where these blue lines on this side come from the other fracture A, alpha, and this is what is in beta and stops there. Now, I will have to explain something about streamlines and equipotentials. There won't be a lot of mathematics, but it's fundamental to understand that what we are doing is simplify the flow in each of the fractures and that's reasonable, that's a very common assumption. Assume that Darcy's law for groundwater flow applies in those planes, that they're filled with some rubble or something. And of course, continuity of flow applies as well, and we have very good ways to solve problems like that governed by Laplace's equation. So groundwater is a matter of energy. So flowing through, I've never tried it, but flowing through rock or little particles, so sand, porous medium, that takes a lot of energy. You have to go through and it's a very crooked path. So you lose energy. And the red lines are called from discharge potential, constant values of discharge potential, and that is a representation of direct energy, that's just straight energy, and it goes down as the flow progresses from higher energy to lower energy. Same thing as electrical. So this is an identical set of equations as we have in electrical current. So you can imagine the blue lines as electrical current flow and a decreasing voltage, the red lines. Now there is a problem that I'll have to explain. So this is, let me first go to plane alpha, where you see it's just the opposite. It is a very simplified model, but I hope that to give you some idea. And it meets the boundary conditions exactly. I'll go back to this, what is really happening a little later on. So these are two intersecting fractures bounded by circles, and we assume that the boundaries are impermeable, that these planes, which are the fractures, are filled with some material so that the flow in there can be reasonably explained by Darcy's law and continuity of flow. And so there's a job we have to do, and that is formally place parameters and variables and vectors and so on at these fractures, intersections, like this is an intersection point, that's another one. And in order to solve the problem mathematically, we need to identify these things, and we do that by unit vectors that indicate coordinate directions in this plane. They're normal to each other. We can make an X and a Y Cartesian system in those two directions which are normal to each other, and then do the mathematics as we normally do in aquifers. It's interesting that we can actually have as many of these intersections, and intersections can intersect other intersections. If you look carefully at all the boundary conditions, that there's no problem with that. It can be really very arbitrary. So this is the red plane. It continues here. And this is a black plane. And you can see it's dashed where they dive underneath another plane. So the point of this picture is just to show you that you can handle these things mathematically in a computer program, and it's been done, that Eric has done that already. So the flow in each fracture is controlled by Darcy's law, which is this. H is called the transmissivity, K is the hydraulic conductivity, which is a measure of how hard it is to flow through, tells you the energy loss. H is the thickness of the thing. The K and the H can be discontinuous, but not smoothly, but in discontinuities. And the hydraulic head is phi. Let me take this thing. I took that. So, and the Y component is the same. Mass balance is just this. That is the divergence of the discharge vector, which is the amount of flow over the thickness per unit time per unit width. The hydraulic head satisfies Laplace's equation, and we write the solution for each fracture as a function of a single complex variable. Now that is what the analytic element method is based on. It's sufficient to write a function, any function that you come up with, as a function of a single complex variable, z is x plus iy, where x and y are Cartesian coordinates, to meet the boundary, the differential equation. That's really amazing, but it's true. So if I tell you log z times the square root of z squared minus cosine z, it satisfies the differential equation. So it's easy to check that your model is right, and there's another way to check it graphically that I'll show you as well. So we apply the analytic element method, AEM, and I'll give you a little history of that. So the analytic element method is based on the idea that I just explained, that it is not difficult to create functions that satisfy the differential equation. It's much harder to create ones that are useful, because that function I just rattled off is not very useful. I don't even know what it represents. So you have to find a way to get useful functions. Now this is a picture that was made by the Nashville district of the US Army Corps of Engineers that we were working for at this time in Minnesota, this department. I'd given a short course for engineers from the district, and they thought that we might be able to help them. This is, the width of this picture is about 48 miles. And we were asked to they had to make an environmental impact statement. This is in the 70s. And they said, why don't you're so smart, so show us that you can make a model of this. Well, the only thing that existed at the moment that could possibly do that was the Pinder-Trescott-Larsen model that the Corps of Engineers has and was given to us. And I had, at a PhD student, one of my early ones, Christine de Tournay. And it's that Christine, indeed. And she came to me and she told me, it's impossible. There's just absolutely no way. Because at that time, the computer we had purchased, it was the first mini computer at the university, with funds from the National Science Foundation. I'll give you the properties. To 56K. 32-bit, that was why it was useful. You could actually do calculations with it. 32K. The disks were huge, like this big. I have them still. 5 megabytes. So, yeah, there was no way. You couldn't possibly even think about doing it. So we were on the contract, so I had to come up with something. So, and I was always very much interested in mathematics and in doing groundwater with a maximum application of mathematics, which I did. And I made these streams, these yellow things, and the center of these, they're sandy areas, sandy geology, and I made what's called line sinks, linear elements that take water out of the system. They existed at the time, but not in this kind of application. So I made that, and it worked. This is a picture of that was made then on a, I don't even want to tell you what kind of graphical device it was. It was huge. And so the contour lines are energy lines, if you like. And of course the flow is again down those lines. And the line sinks that actually take the water out of the system are these black lines. And the bulges are the result of infiltration that's occurring. Now then in 2000, so it was quite a bit later, this is work by Igor Yankovic, not your first PhD, but early-ish. And he made this picture, these 4 pictures. In 2000, there was an analytic element conference in Brainerd, Minnesota, and the left picture is 100,000 impermeable disks. Then you take the little square in the middle, you blow that up to the next one, so the arrows tell you where we're going, and you see now beginning to get shape. Then we take the next square, go down to the left, and it begins to look like flow in between disks. And then on the final one on the right, you can see that it is really very accurate. Now those are the properties that we are going to use in this model that I'm proposing, where I think we can really deal with 100,000 fractures intersecting. And there are all kinds of reasons why that's possible, but it's basically possible because of the analytic element method. Characteristic for that method, because there are others that look like it, boundary element methods and boundary integral methods, but they're different. And the difference, it has taken me years before I really realized what the main difference is. Each of these elements is completely isolated from the rest. They have no connection whatsoever. They don't know about each other. They will affect each other, but indirectly. So they're completely separate. And this model of the fractures that I'm proposing is also completely independent. These fractures are they only know each other where they intersect. So it's really ideally suited. I should say, by the way, this is published in Journal of Hydrology. It came out 2 months ago or something like that. And all the mathematics is there, but I'm not going to show you. This is an application in a computer program called MLAM, Multi-Layer Analytic Element Method, and, or model, whichever you like. This is just to show you what you can do. This is one of the things you can do very well with this, is deal with scale differences. You see, it says here on the bottom, this is 600,000, 700,000, so there's 1,000 kilometers distance between those. This is Nevada, a big part of Nevada, California. It's a huge scale. And you can still go this is the desert, Death Valley, but you can also zoom in, and that's really very nice. It's almost impossible to do with anything else. Just recently, this program that was used for that and went through quality assurance of the Department of Energy, I think it was. Yeah, the Department of Energy is now available on GitHub, and I say that because my students are now modeling with it and actually doing quite well. So it's very useful for students, this kind of a program where you can see things, you can see what happens if you move things, change them. So anyway, so to just show you why the analytic element method is suitable for this, it's very, very accurate. It goes really, this is 2 canals that take water out of the system, and they're almost touching. They're millimeters apart. It's the kind of problem that when I started, couldn't even think about. This is a close-up, and you can see, if you understand it, the red lines are energy, and they're constant along those black lines, and you see they're perfectly constant, and the blue should be normal to it. And that high degree of accuracy that can be locally achieved is necessary, makes this suitable for study. So to model intersections, you have 2 conditions. So this is really, now we're getting down to what you have to do to solve the problem. So first of all, continuity of flow. So where they intersect, there's water going from the one fracture into the other fracture, and the totals must match. And the second one is continuity of hydraulic head. You don't want to have a jump in head between parts of that intersection. So there are elements that add or remove water in each fracture. There are ones, so there are heads given sometimes along creek. So when a fracture intersects a creek bottom, that provides water. Wells intersect, as you saw in that one picture, I showed multiple fractures, that's fine. That's no problem. This was I gave this talk some time ago for the local groundwater people, among which is Justin Bloom, formerly from the Department of Health, who is retired now, but he's still doing work in karst and fractured flow. And he told me that what is really strange, if you look at the intersections through the rock and through openings of the wells, that the wells don't look circular. Well, you can see that if you're at an angle, which you're bound to be, then of course the circle is not a circle, but an ellipse. So there's a bounding, an impermeable ellipse or circle. So that too, in the fracture that's bounded by that circle is an independent element. It's not part of the fracture, it's just added on to enforce the condition that there is no water going through that impermeable boundary at the outside. So I'm going to show you a few functions so that you can see that it's not that terribly complicated. Well, that function chi is a little bit complicated, but omega is the complex potential. That real part is the potential. The imaginary part is the stream function. Chi is a transformed variable. all these coefficients, A, alpha, comma, M, N, are complex, and the A alpha represents the plane, the fracture that it's in. M is the intersection number, so all of these things have to be labeled carefully and so on. So that's the function we're dealing with. So these A's are the degrees of freedom. You can have thousands of them. So the conditions are now explicitly stated: continuity of flow and continuity of pressure. So it's important to know. Oh, let me first show you the element. So this is a trick that we're using in analytic element method. So the line, so the intersection is a line, like I show on the left picture. I've given it two sides because one side is in the one fracture, the other side is in the other fracture. So they're really different sides. And when you transform this, do a conformal map onto a circle, which is a classic, very well-known mapping, then the red is on the upper half and the black is on the lower half. So it's very nice to deal with inhomogeneity, with jumps, because they're so different. On the line, it's difficult to know where you are. Here, it's clear. I mean, you're on the plus side of the circle or on the negative one. And the function that does that, just for completeness, is this: to go between the physical plane, the capital Z, and the sky plane, which is just fantasy. So the physical plane looks like this, of that element, simplified, with these ellipses being the equipotentials, and the transformed plane is like this. And I need to explain something, otherwise it's hard to understand how this all works. So if you have the stream function, it's constant along streamlines, and the difference in value between two streamlines is equal to the difference in the stream function is equal to the flow in between. That causes problems, because if I start and go around this circle, I start with C is 0, I go a little farther to 90 degrees, and I get Q over 4. That's how this works, because 1/4 of the flow has now been recorded between this point and this point. If I continue, then I get to Q over 2. Q is the discharge, the total going into that blue circle. And if I continue, well, I'm now on the negative side. So on this point, it's minus Q over 4, and when I'm completing it, I end up at minus Q over 2. So there is a jump in the, so one of them is minus, the other is plus. There's a jump in the stream function. So that is a problem in these things, except that in this case, that's critical and very useful, because we need that jump, because it tells us how much goes in there, and I want to apply the condition of continuity of flow, preferably exactly, and I can do that with this problem, which isn't really a problem. So continuity of flow along the entire intersection is exactly met. There's no, so from the start, it's exactly met. The coefficients are chosen in such a way that that works. And the continuity of pressure is not exact, but in a least square sense, very closely met along the intersection. So there are a few equations I want to show you. So when I write these functions, that was that series that I showed, there is so the alpha refers again, just like before, that's the crack number, the pressure, I should say the fracture number, that's the intersection number, and so they're all labeled, and then this is plane beta. So you have the image of the one is on the other plane. So that mu is the jump in the stream function, and that tells you the amount that is the jump that's lost from the one plane going into the other. So the boundary condition, just for completeness, the jumps must be opposite in strength, because the jump in the one must be minus the jump in the other. So all I have to do is choose these coefficients so that for the beta plane they are the same as the alpha plane except the other sign. That's not very difficult to do, of course. And the discharge is the same thing. So it's hardwired in the solution. I don't have to solve for it. I don't have to worry about it. It's always met. And then, of course, we use this already chosen set of coefficients to meet the condition of continuity of head. This. So it's this condition is met in a least square sense. Okay, this is a set of these fractures. I mean, I still can't see it, but Eric made this picture with these circles, and he's now producing these things in hundreds and many hundreds of these fractures and do this. So what you see in each fracture, each of these four, is a set of equipotentials and streamlines showing a mesh of small squares or approximate squares. That will tell you that the differential equation is met. We also can trace flow from one of the fractures into another. So there are four fractures, and I labeled them alpha, beta, gamma, and delta. I'll just trace one of them. This is the source, S. Water going from S, there's flowing here in this plane, going to a connection with alpha, so this is a connection. And I go to plane gamma, so I come out in gamma here. Then I hit this intersection with beta. No, I didn't want that. I hope, I was here. Ooh, I better keep my other finger out of the way here. So it's flowing from alpha, we were here into gamma, this is coming from alpha in gamma, flowing to beta, I come somewhere out of beta, this is from gamma, so I'm going here, and then end up at delta, where I end up at the well. So it's tedious, but these things are all recognizable because of the stream function value, so I know exactly which one is which, and I can trace them through the whole system. Okay, these are equipotentials and streamlines just to show that the differential equation is met. So let me show you, so these are a few more of these, but they don't mean too much. This is a set of these things. And you see how they work, but it doesn't tell you much, but it does tell you that it's possible to do these things. I'm about right. I should stop soon. So I'll show you an animation that Eric made, and then I'll leave this over for questions. Oh, I hope I didn't stop the meeting. This is so silly. Where is Zoom? I may have screwed up. Yeah.
I think you're all good here.
Yeah, am I still there?
Yep, you just have to open.
Okay, good. Yeah, okay. Well, I do.
You back at the beginning. Do you want to continue, or are you?
Yeah, no. I want to actually pause this presentation
I see. Okay.
and show something else.
Okay. So see the. Yep.
Yeah.
We're still
I'm certainly glad you're here. Okay.
Happy to help. Happy to help.
Yeah. Okay.
Okay.
If you can minimize this, there are a few things I just want to show.
Within the presentation or no?
Well, I want to show it, but not with. It's not part of this presentation.
Okay. We can just minimize the presentation.
Yeah, that would be good.
Okay.
And then if I can go, I just go to. Yeah, here. I think this is enough. So there's a small one. Eric made an animation because it's so difficult to see these things.
Okay.
So you get a bit of an idea. So you see all these circular fractures, and it's really complicated because they intersect. And the flow, tracing the flow, of course, it's a nightmare. But we can do it, and we can do lots and lots. You've seen the 100,000 disks. This is the same. We can do hundreds of thousands. So the idea that I really have is that we develop. I'm going to NSF, hopefully get some money to do that, but use machine learning to learn how this works. What kind of, if we want to do this as a continuum, what scale? How many? Where can I do that? What is the REV or RVE that I have to adhere to in order to go to a continuum? That continuum, does it have a hydraulic conductivity? Is it a tensor? Is it symmetrical? And none of these things we don't know. We know nothing about this whole system. So the idea is to do these runs, many, many runs, and learn. So the interesting thing is that if you do a run, if you solve the problem, you only have to do it once. So given a certain system, you solve it once. You have the coefficients. And then you can do runs, flows and tracing it very cheaply because all the coefficients are known. And it's called embarrassingly parallel. You can do them if you have 10,000 of these things and you have 10,000 processors, you can do them all at the same time. in the phase of doing the runs. In solving it, it's not quite as nice, but close. This is, we call it superblocks. This is the ideal environment for superblocks. So this is, I think, a very useful way to do it. Also, for the completeness, I will show you the large animation Eric did. And then I'll stop.
Can
So-
you maximize the picture, or is this the size?
I think this is the size. Yeah, no, it won't do the. Do you think you can do
Let's
this?
see here.
Oh, yeah, very good. The plus should actually give it away. But you see, I don't know how many these are, but you can really do lots and lots of those. So I think I'm really excited because think of it, you have these large numbers, it's a huge model, and I can trace. We are now, the second paper we are working on at the moment is to trace precisely in this model where something is going. So I'm really excited, which is why I wanted to give this presentation. Okay, so.
Take over the role.
Yeah.
Your microphones are on. Questions?
Can I just ask? Okay. Thank you also for the nice talk. I have a question. In the real physical world, if two fractures are very close to each other,
Yeah.
will there be flow happen between the fracture? Because once you have fracture, the tip of the fracture will have micro cracks.
Yeah. Yeah.
So flow may still exist even
Yeah.
though they don't touch each other but very close to each other.
Yeah. We can put in the microcracks.
Yes. Because you show that the picture, the two cracks,
Yeah.
two fractures very close to each
Yeah.
other, you do have streamline
Yeah.
right in between. Is that reasonable to put the micro cracks to
I
let
think
it
what we
communicate?
should do is actually put in the microcracks
Yes,
physically.
yes.
But another phase of the project would be to try to see what we can do with the rock, making it permeable. But it mostly is, I think, certainly for the numerical testing, I would prefer to make the actual cracks. It's very small cracks, put them in the model.
But that would be a zone of micro cracks with a length scale, though.
Yeah, yeah.
Okay.
Well, as I said, we can do hundreds of thousands of these things, so there's really not a limitation
Okay.
in the size. Because, and the beauty of the model is that when you focus on that, and let's say that we have 10,000 of these small cracks, the rest is no longer there. You don't see it. It's there, but we can represent the far field with a very simple expansion.
Okay.
So that is I didn't explain all of that, but the point is that you can do everything that's farther away than close, which you have to define, of course. All of that is captured in a single expansion.
Okay.
And we have a way to determine the coefficients of that.
Okay. Thanks.
But it's a very good point. And when you get very close, of course, that can be.
Yes.
Yeah. go ahead.
Thank you very much for the talk. I'm curious about whether based on my understanding, is kind of using complex variable,
Yeah.
which is particular efficient for the specific geometry of the fracture. So I'm wondering whether it can be extended to other shape of the fracture, for example, like a rectangular or other different geometry.
Well, up to a point. It depends. But there is a certain freedom in the shapes.
Okay.
So we have, for example, made curvilinear elements for rivers, that sort of thing, where there's a certain shape built into that curve. And in the 3D planes, I would have to think about that, but there are no fundamental block. to what you
And
can do.
I still have follow-up question. I personally interested in the dynamic fracture, so which means the fracture can be expand or have a
No. No, this is not. But we can make it transient, so it can flow dependent of time. But it's not. The water cannot expand the rock, so there are no high pressures. It's just limited to flow. As I said, groundwater recovery, just flow through the rock. The rock's already there. You're not going to make the crackers bigger or smaller or any of that.
Okay, thank you.
So that's beyond this. The goal is different. The goal is, I don't think I repeated the question very well. Okay.
Any other questions? I'll ask one then.
Okay, good idea.
You showed us some amazing, cool little cartoons.
Yeah.
And I've seen cartoons like that. How good currently can we actually, in a field setting, identify fractures? Is this just a cartoon? Or why do we know that fractures might look like that? Or how good are we at, I don't know, looking into the ground and determining what fractures are there?
Well, there is, especially in Sweden, because they have lots of them, because it's all granite, and so they have to deal with fractures all the time. But and I don't have personal experience in that, but the approximation of a plane for a fracture has been adopted by quite a few people, and seems to be a reasonable approximation. But of course, it is an approximation. But yeah, no, that is generally the accepted.
Any other questions? Are there any questions from outside the world? No. Okay. Well, in that case, let's thank Otto again for his presentation.
Thank you.